So it's useful to use a Taylor polynomial to approximate the function value of a curve. We need to know what the error is and how close it actually could be to the real one. So let's consider f of x is equal to the natural log of x. The first step is just a little bit of review. I want you to find the fourth degree Taylor polynomial. So find p sub 4 of x about x equals 1 for f of x is equal to ln of x. So let's just kind of start and review the process. I want to do, I know f of x is ln of x, and let's do some successive derivatives. F prime of x is equal to 1 over x. F double prime of x is equal to negative 1 over x squared. F triple prime of x is equal to, this would be 2 over x to the third. And I know that f quadruple prime of x is equal to, this is really 2x to the negative third, so this would be negative 6 over x to the fourth. Then we want to figure out f of 1, which is 0, f of 2, or sorry, f prime of 1, which is 1, f double prime of 1, which is negative 1, f triple prime of 1, which is 2, and f quadruple prime of 1, which is probably better expressed as f with the parentheses 4 at the top, because that means fourth derivative is negative 6. Then we're going to figure out the fourth degree polynomial. So I know p sub 4 of x is equal to, so we start with f of 1 plus f prime of 1 times x minus 1 over 1 factorial plus f double prime of 1 times x minus 1 squared over 2 factorial plus f triple prime of 1 times x minus 1 cubed over 3 factorial plus f quadruple prime of 1 times x minus 1 to the fourth over 4 factorial. Let's try to simplify this down. F of 1 we set up above is 0. F prime of 1 is 1, so this just becomes plus x minus 1, and 1 factorial is just 1. Plus f double prime of 1 is negative 1, so we get negative 1, x minus 1 squared over 2 factorial, plus, then I have 2 x minus 1 cubed over 3 times 2, and those 2's are going to cancel. Then we have plus, let's see, the final number was negative 6, x minus 1 to the fourth over 4 times 3 times 2 times 1. So simplifying that down, I get x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus the 6 and this are going to cancel and give me x minus 1 to the fourth over 4. So clearly you see a pattern here. So that's the kind of, when I say find the fourth degree polynomial about x equals 1, that's the process you follow. Part B, I'm going to ask you to approximate the natural log of 2. So we're going to use this polynomial to do p sub 4 of 2, which is equal to 1 minus 1/2 plus 1/3 minus 1/4. And if I add those together, I get 7/12, and the decimal approximation would be equal to, or actually the exact value would be 0.583 repeating. Next, we're going to ask, what is the maximum size of the error? Well, given that this sequence is an approximating sequence, or sorry, alternating sequence, plus minus, the max size of the error would be a sub 5, the fifth term, and a sub 5 is equal to 1/5, which is equal to 0.2. So I'm going to put a little note here with a little hashtag that this is alternating. And I got to pause. Yeah. Okay, part D is asking now, what is the actual error? So to get what is the actual error, we would need a calculator to give us the actual decimal value. So what is the actual error? Give us the decimal value of the natural log of 1, or of 2. So in a calculator, we would type in the natural log of 2. Then I'm going to subtract the approximation that we have from up above, because we are approximating it to be about 7/12. And when I punch that in, I get about 0.11. So that is my error. It's somewhat close. I mean, you can probably hypothesize as to what we could do to make it a closer approximation. But lastly, I want to figure out for what values of x will P4 of x approximate the natural log of x with an error less than 0.2. So what this is kind of referring to is that we have this polynomial up above that's centered at x equals 1. So it's about x equals 1. And obviously the closer to 1 we get, the better the approximation is. But the further away from 1 we get on either side, the less good this approximation is. So I want to figure this out. Well, P4, I'm just saying specifically we're going to use a 4th degree polynomial, so I know that the 5th term, a sub 5, is equal to x minus 1 over 5 to the 5th power. And I want the absolute value of that term to be less than 0.2. That gives me an error that will work. Well, if that's true, let me multiply both sides by 5, and I get the absolute value of x minus 5 is less than 1. Or if I raise both sides to the 1/5 power, x minus 1 is less than 1. And if the absolute value of x minus 1 is less than 1, that means that x is contained between 0 and 2, if you remember your absolute values. Just to remind you, that means that x minus 1 is less than 1, and x minus 1 is greater than negative 1, which basically means that x minus 1 is between negative 1 and 1. So if I kind of flip that around, negative 1 is less than x minus 1, which is less than 1. Add 1 to all 3 sides, and I get this. So that's what this is saying. And that means that this approximation is good within 0.2, but only for x values between 0 and 2. So I'm going to go back up and retitle this at some point. This is not only Lagrange and Taylor's theorem, but this is about approximations. And how good is my approximations and error. So I did that with an alternating series, but not all Taylor polynomials are alternating. So this section really focuses on the remainder of a Taylor polynomial. So I'm going to state this, and this is going to be a little confusing at first. You're just going to kind of have to go with it for a little bit, and then we'll start to work some problems and see what you're actually going to end up doing. Given f of x, a function is equal to a polynomial. So this right here is the Taylor polynomial, which is an approximation, plus a remainder, r sub n of x. And the remainder is really just the difference between these. So we know that the absolute value of the remainder is equal to the absolute value of the difference between f of x and p sub n of x. So what I'm doing with this is I'm really just defining what I mean by r sub n of x. That's the difference, and that would actually be this value right here. That would be like an r sub n of x, because that's the difference between the actual and the theoretical. Specifically, that's r sub 4 of x. So I should probably put a little 4 there. That's the remainder of the 4th degree Taylor polynomial. So back down to here, Taylor's theorem says that if a function f can be approximated by a Taylor polynomial, I'll say by a Taylor polynomial of order n. So that's what we've been doing. We've been approximating the one up above with a polynomial of order 4, so of order n, with an interval of convergence I containing C. And this interval of convergence containing C, I want to kind of talk about for just a second. That's kind of what we established right up above when we had this interval of convergence. This right here is an interval of convergence. And it describes an interval of convergence because it tells me where it is within the error that I want. So anyway, with an interval of convergence containing my C value, in this case C was 1. So if this is all true, then what I can say is there exists a Z between X and C, so between my actual value and the value that I'm centering around. Remember that what I'm really doing here is this is like an interval of convergence right here, and I'm centered around C, and I'm trying to find the f of x value with an approximation. This is saying there is some Z in between there such that f of x is equal to p sub n plus r sub n. This is what we set up above, and which is equal to p sub n plus the n plus 1th derivative of the z value over n plus 1 factorial times x minus c to the n plus 1. This right here is called the Lagrange remainder. This will become a little clearer here in a second. I know that this polynomial right here, this whole idea, is really just equal to f of c plus f prime of c times x minus 1 plus f double prime of c times x minus 1 squared, or x minus c, sorry, not x minus 1, x minus c, we're centered around c, over 2 factorial, and so on. That's just the Taylor's polynomial. So what this is actually saying, that's the end of the theorem, but what this means is that the goal is not to find z. We don't want to do that. I mean, if we did that, we would actually not have to approximate at all. Our goal is not to find c. Our goal is to find a bound on r sub n, to find kind of a maximum thing that it can do. So what we're really going to do is we're going to say this remainder, r sub n of x in absolute value, is less than or equal to x minus c to the n plus 1 over n plus 1 factorial times the maximum value possible of the n plus 1th derivative of f at z for a z in between x and c. Okay, that's probably confusing as heck, and I get that. Let me show you how this looks step by step so you can model this when you do your work. Let's start with f of x is equal to sine of x. This is a Taylor polynomial that we actually have done, and without deriving it, I'm going to say that this sine of x is about approximately, let's just do a third order polynomial. And a third order polynomial means third degree, and that's just x minus x cubed over 3 factorial. This right here you can get from a few places. You can derive the Taylor polynomial, which we did up above with the natural log of x, or you can start to memorize the polynomials that you're going to need to know. E to the x, sine of x, cosine of x, natural log of x. You're going to want to know all of those. So coming back to this, step A is that we want to approximate f of 0.1 using p sub 3 of 0.1 and determine the accuracy of this approximation. The first part is easy of this. I know that sine of x is about 0.1 minus 0.1 cubed over 3 factorial, which means that the sine of 0.1, I should just say 0.1, not sine of x, is about 0.1 minus 0.001 over 6. If I get a decimal approximation for that, this is about 0.099833. And I know many of you are thinking, why am I doing this? Like, what is the point? I have a calculator that will actually calculate the sine of 0.1. But your calculator only calculates the sine of 0.1 by doing this. So let's get back to this. I've got an approximation. Let's determine the accuracy. I'm going to actually slide this down here to part B and move the and determine accuracy down here. So I've got this as a separate step. That way you can track what we did a little bit later a little bit better. So given this, determine accuracy, we're going to say r sub 3 of x equals the fourth derivative of z over 4 factorial times x to the 4th power. Now, why x to the 4th power? Well, because we are essentially centering this. This is the Taylor series representation at c equals 3. Remember, when c is equal to 3, we call this a Maclaurin series, or Maclaurin polynomial, not Maclaurin series. So at c equals 0, so I'm going to kind of carry that down here. I know that my c value is 0 because that's, I'm basically at sine of 0.1. I should use a c value of 0 in order to really get this. Okay, so that starts with the c value. That means that this x to the 4th was really x minus 0 to the 4th. Okay, so what does this mean right here? F the 4th derivative of z. Well, let's kind of go off to the right side and talk about the sine of x. And if that's f, if f is the sine of x, this isn't going to be as bad as you think it is. If f is the sine of x, what is the first derivative? That's negative cosine x. The second derivative, negative sine of x. The third derivative, that'd be negative cosine of x. And the fourth derivative is back to the sine of x. So I know that the fourth derivative is the sine of x. I know that my c value is 0, and I know that my x value that I'm trying to find is 0.1. So what I'm basically saying is in between 0 and 0.1, what is the max value of f4 of 0.1? So this is basically saying what is the maximum that could ever be. If I was doing this in a calculator, I wouldn't have to. I would actually say the max value is the sine of 0.1. But the max value of sine is 1. The max that it could ever be. Sine's biggest value is 1. So given that, I'm going to replace all of that with 1. And I'm going to say that a remainder has to be less than, it has to be less than 1 over 4 factorial times, and x to the 4th is 0.1 to the 4th power. And if I clean that up, I get that that it's less than 0.0001 over 4 factorial, and that is about 0.000004. So that's the idea behind this. We're trying to basically use this formula here to figure out what's a bound that we can create. Okay, next. Let's go to part B. Or part C, technically. Is P sub 3 of 0.1 an over or an underestimate? To do that, you have to have some knowledge about Taylor polynomial for sine. Let's look back up at the Taylor polynomial for sine. X minus x cubed over 3 factorial. It's a positive term and then a negative term, and it's going to continue with a positive term and then a negative term, positive, negative, positive, negative. So since the last term is negative, it is an underestimate. I'm going to say underestimate because the last term is negative. And finally, D, I want to give an interval where f of 0.1, which is equal to sine of 0.1, must be bounded. So I'm going to give an actual interval where it must be bounded. Well, if my error is this, and I know that the sine of the 0.1 was about this, and I know it's an underestimate, this 0.099833, which was an underestimate, must be less than the actual sine of 0.1, which must be less than 0.099833 plus the 0.00050 and the 4 must be between that and the error. So if I simplify that, I get this. Let's see, 0.99837. Technically speaking, I should have actually subtracted the 0.004 from this, but since I know it's an underestimate, I can put that as the bottom one and keep sine of 0.1 in between that. So this is giving me, I mean, I know the sine of 0.1 now is 0.09983 something, and I have a very good idea of what the value is without actually calculating the sine of anything. That is cool. That is an amazing, amazing achievement to be able to get the sine of something that close without actually doing any trig. Let's show how this works for e to the x. So f of x is equal to e to the x, and I know that the 4th degree polynomial of this p sub, well, let's do the 3rd degree one, p sub 3 of x, let's not do 4th, let's do 3rd degree, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That is the 3rd degree one. So we're going to say that this is given, although you can calculate that and find that on your own if you'd like. And what I'm going to do is we are going to approximate f of negative 0.4 and find the error. So this is going to be a quick process. You just have to know what to do when this question comes. So we're going to do p sub 3 of negative 0.4, which is 1 minus 0.4 plus 0.4 squared over 2 factorial minus 0.4 cubed over 3 factorial. You can take a calculator. An interesting thing would be to give you a 4-function calculator and actually ask you to do this. Oh, that would be fun, and I'm considering that. So I get about this. I get about 0.66933. Next, I need to say that the remainder, r sub 3 of x, Specifically r sub, well, let's do r sub 3 of x. That has to be equal to the fourth derivative of some z value sorry, it's hiccuping a little bit, divided by 4 factorial times x to the fourth. Remember, this is what the remainder is equal to, and we're going to try to do is set this remainder less than or equal to some max value of what that would be. It's also sometimes helpful to kind of set your c value. This is only true when c is equal to 0, because then it's x minus 0. And z here, we don't know. That's not the point. I want to figure out what f of z here. And x here is 0.4. Oh, sorry, negative 0.4. So let's off to the right side start listing the e to the x. Well, what's the derivative of e to the x? I think we all know that. I was kind of hoping for some response from the room there, but no. So the derivative of e to the x is e to the x, and the derivative of that e to the x is e to the x, and I know that the fourth derivative of e to the x is e to the x, so we can kind of carry that all the way down and say the fourth derivative of x of e to the x is e to the x. And the max value, which, remember, this fourth derivative is basically saying the fourth derivative of e to the x is the max value of e to the x between my x value, which is negative 4, and my c value. So the max value of e to the x between negative 0.4 and 0. That's what I'm looking for. That's what this inequality establishes, times negative 0.4 to the fourth over 4 factorial. So what is the max value of e to the x between negative 0.4 and 0? Well, here's the graph of e to the x. And between negative 0.4 and 0, the max value of e to the x occurs at x equals 0. The max value of e to the x between 0 and negative 4 is e to the 0th power. So e to the 0th power times this negative 0.4 to the fourth over 4 factorial. Negative 0.4 to the fourth is let's kick that back, 1, 2, 3, 1, 2, 3, and then 1, 6. Is that right? 1, 2, 3, 4. Yep. Over 4 factorial, and that's going to be about 0.00107. So that's the cap on the remainder right there. Okay, next, number 4, the last one. Let's determine. This is going to be on determining the values for x within a given error tolerance. Much like we did before. So within a given error tolerance, we're going to kind of do that. So let's just do the same type of curve. F of x equals e to the x. And I'm going to do a better job of saying at c equals 0. So that this is now the Maclaurin polynomial, the special Taylor polynomial centered at c equals 0. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And we're going to look at this for x less than 0, so negative values. And the error tolerance, I want the error, want error to be less than 0.001, 1/1000th. Okay, so if I want the error to be that, well, let's see what the error is. R sub n is equal to, of x is equal to, this is the reminder of what the general one is, the n plus 1th derivative of some z value in between x and c, divided by n plus 1 factorial, times x minus c to the n plus 1. So this is for a general Taylor one. For Maclaurin, we can just simply replace the c value with 0, and we can talk about some z value in between x and 0. So this is just x to the n plus 1. So I know that that means that z is in between x and 0. And up here, z is in between x and c, for whatever c value we have. Okay, so let's kind of keep this going. What else do we know about our special case? Well, I know that f to the n plus 1 of x equals e to the x when f of x equals e to the x. So that right there is crucial. If I'm talking about e to the x, then no matter what derivative I'm talking about, then we have it. And I also know that the max value of e to the x on any x is less than or equal to 0 is e to the 0, which is 1. We already established that before because e to the x increases, and its max value when x is less than or equal to 0 is 1. The most it ever reaches is 1. So that means I can kind of create a bound on this, and I can say that r sub n of x is less than, 1 times n plus 1 over n plus 1 factorial. So that's kind of the key here of how we're going to do this. Now I'm going to just look at the third degree one. R sub 3 of x is equal to, or is less than x to the 3 plus 1 fourth over 4 factorial. So that's what I want, and I'm going to create the absolute value because my remainder is actually within an absolute value region of that. And I said that I want my remainder, my error, to be less than 0.001. So this is what we're going to solve. Let's multiply both sides by 4 factorial. 4 factorial is 24. So I get x is less than 0.024. Then I take a fourth root of both sides. And remember, if this is absolute value, I want to create a bound on what this could actually be. So if I've got the absolute value of all that, and I know the absolute value of x to the fourth is this, but if I create a bound and I raise to the 1/4, I'd want the absolute value of x to be less than the fourth root of 0.024, which is 0.3936, or about. So that means that negative 0.3936 is less than x, which is less than 0.3936. But we can do better because I said that x has to be less than 0. So less than x is less than 0. And that creates a bound of tolerance on that. So your homework for this is going to be, let me write this down, 9.7b. Well, you can look it up. I'm going to let you look it up because I don't know in the future where I'm going to have the homework be. So good luck.